Good morning, ladies and gentlemen. This lesson is going to talk about implicit differentiation and related rates. No pun intended, the two topics are closely related. When we do implicit differentiation, most of the time, we're going to use the operator d dx. When we do related rates, we have to talk about the rate of something, the rate of some distance changing over time, over a change in time, and this is why we're going to use d dt when talking about related rates, and that dt is going to be our change in time, which will give us a rate. And in fact, our example 1 this morning, we're going to be looking at a related rates problem. Then the problem is this. A bug is crawling on the graph of y equals x squared minus 3x, such that the rate the x changes is 2 centimeters per second. This is key information. What we want to know is the rate that the y is changing when x is equal to 3. This statement here is going to be remaining constant in our problem. The rate the x is changing is always going to be, for this problem, 2 centimeters per second, meaning the bug is going to be crawling to the right. The x values will be increasing since the rate the x change with respect to time is positive. So let's look at the graph of this and describe what's going on first. Here I have the graph of y equals x squared minus 3x. This graph has two x-intercepts 0, 0, 3, 0. And we're going to demonstrate what's happening first. This is what is happening. I have a bug, and he is crawling on this graph, and he's crawling to the right. And his right movement is changing at a rate of 2 centimeters. If I can get that, 2 centimeters per second. What I want to determine at x equals 3, what is this creature? What is the rate that the y is changing? I do know, if I just watch this bug again, we'll do the same bug but in a purple suit. Over here, this bug is crawling down, and so therefore dy dt would be negative over here. But he's crawling down and to the right, down and to the right, down and to the right. Then about right here, he starts crawling up. He's still crawling right. So since he's crawling up at x equals 3, we would assume, or we won't assume nothing, we will know for certain that at x equals 3, this rascal that we want has to be positive. I think I have that outlined on the next slide. Let's check out the next slide and see what's there. So here's the next slide. Same problem. I have some extra work. And this is exactly what I outlined, is that the dx dt is 2 centimeters per second. The bug is crawling to the right at that rate. At x equals 3, the bug will be crawling up and to the right, and therefore, since he's crawling up, that tells me that dy dt is going to be greater than 0 when that little rascal is right here at x equals 3. He's going to be moving to the right and up. To the right is the 2 centimeters. That's how fast he's going to the right, and what we want is the rate he's moving up. So let's get to the analytical work, since we had a little graphical explanation. Okay, I graph. Let's do it. Cover it up. That way I can pull it down as we go. Same problem. And here we're going to get into some analytical work here, down here towards the bottom. Okay, I have this creature right there. In order to get dx dt, I'm going to need to ddt it. And I want the dy dt. So that is why I choose the operator ddt. I'm going to ddt both sides of this equation. The left side with respect to t, the derivative of y with respect to t, is fairly easy. It's just dy dt. This one also is fairly easy, and this is where, no pun intended, the bug lies in this problem. If I'm just ddxing, these guys will have no rate attached on the end of them. But I'm not ddxing, I'm ddting. I'm ddting something in terms of x. So we're going to treat that just as we did differentiating y with respect to x. So please don't make this difficult. It's kind of straightforward. So if I d dt y, I get dy dt. If I d dt x squared minus 3x, this is the derivative I want to find with respect to t, I'm going to get 2x, which is the derivative of x squared, with the dx dt tagged on the end. If I differentiate negative 3x with respect to t, I differentiate this piece with respect to t, I get negative 3 with the dx dt tagged on the end. To review, I'm going to d dt this piece x squared. That derivative is 2x with the dx dt tagged on the end. Now, if you look, all I have to do to finish this problem, all I have to do is substitute what we know, what we were given. What were we given in the problem? We were given that x was 3 and that dx dt was equal to 2. Let me clarify that that is a dx dt that we were given. And I'm going to substitute wherever I see a dx dt, I'm going to put a 2. Looks like I see one there. I see one there. This is already a 3. I have a 2. And then I want, when x is 3, I put x equals 3 in. I do some quick arithmetic. 4 times 3 is 12, 3 times 2 is 6, 12 minus 6 is 6, and we do indeed see, the last thing I will say about this problem is this particular value is greater than 0. So yes, indeed, the bug is crawling up. Not bad. You may review this particular problem again if you so desire. Let's go to the next example on this video. And the next example is going to deal with simple implicit differentiation. The problem asks me, find the equations of the tangent lines and the normal lines to x squared plus y squared equals 25 at the point negative 3, 4. To make this grammatically correct, I want to find there's only going to be one tangent line, and there's only going to be one normal line if I'm only talking about one point, as I am. So this is the graph that I have right here. This is the graph of the circle with the radius 5. This radius out here is 5. And I'm looking at the point on this circle, negative 3, 4. And if I put the negative 3, 4 into the equation, it does indeed satisfy the equation. Negative 3 squared plus 4 squared does indeed equal 25. So what I'm looking for on this problem is the equation of the tangent line and the normal line to this point right here. And I think the next slide demonstrates the lines that I want to find. And it does indeed. This is going to be the tangent line to that circle at that point, negative 3, 4. And then the normal line, we remember from previous discussions that the normal line is the line that is perpendicular to the tangent line at the point of tangency. So these two lines at the point negative 3, 4 better form a perpendicular line. We know that two slopes are perpendicular if their product is equal to negative 1. So what I'm going to have to find, if I want the slope of a tangent line, the slope of a tangent line, if I'm talking about XY land, MIN, everything I graph in calculus at this stage of the game is graphed in XY land. So whenever I talk about tangent lines, I have to be talking about dy dx. This is how we denote slopes of tangent lines. And my goodness gracious, we've been talking about that for months. So how am I going to get a dy dx? I'm going to use this operator right here, d dx. And take note that the tangent line, something else that we've done for multiple days, multiple months, the equation of the tangent line at the point negative 3, 4 is going to be the y value plus the derivative at that point, negative 3, 4, and then x minus the x value. This is something that should be in our toolbox, equation of a tangent line. So let's find this rascal by first finding dy dx. Let's go to the next slide. I think down below here we have some analytical work. We do. So if I start with the equation, x squared plus y squared is equal to 25. My goal is to find dy dx. If I'm going to find dy dx, I'm going to d dx both sides. I'm going to d dx this piece. And since I'm d dxing something in x, I don't have to tag a rate on the end. It's just going to be dx over dx, which turns out to be 1. And we know what the derivative of x squared is with respect to x. We've done that like since day 1. That piece is going to be 2x. And now this, if I'm going to differentiate y squared, that derivative is going to be 2y plus dy dx. I have the 2y. Since I'm differentiating ay with respect to x, I need to tag this dy dx on the end of that. And we know the derivative of a constant is 0. We have actually found this derivative multiple times. And if you're ever given a circle, you can, it is common knowledge that the derivative of a circle is negative xy. If you want to put that in your toolbox or put that in a seat on your school bus, you could do that as well. Or just simply find the derivative quickly. And what I did here was just a series of algebra steps. Subtract 2x, divide by 2y, you get negative xy. Makes this problem kind of handy. Now recall, what did I want? I originally wanted the tangent line at negative 3, 4 to that circle. That's going to be 4 plus this dy dx thing at negative 3, 4 times x minus the x value. I put negative 3 and 4 into my equation for my tangent line. Negative makes it positive over 4. And so my tangent line is 4 plus 3/4 times x plus 3. Do not simplify that. Leave that rascal as it is. And that makes it very handy to find the normal line. The normal line simply is going to be 4 plus negative 4/3 times x plus 3. Since these two slopes, 3/4 and negative 4/3 equal -1. So that's going to conclude our small presentation on implicit differentiation and related rates. Hope it helps. I'll see you soon.